I was saying, this is the first seminar of a series, and François, in a sense, benefit of being the first talking about cosmology in the coronavirus age.
It's not the blank page, it's the coronavirus page. Well, so it continued to be very interesting to be in Napoli. In addition to the great food, the sfogliatella in the morning, now I had a mad taxi driver, which succeeded in going faster than 100 kilometers per hour this morning, driving with at one hand, showing me a guitar player with the other hand, and the music blasting, you know, stronger than I could ever be permitted in my house, playing Led Zeppelin. Okay, so I mean, this is, you guys are living in a place where things are intense. It's good.
Either black or white.
Yes, I mean, I don't comment on this, but anyway, so yesterday, for those that were here, we covered essentially what Planck is saying about cosmology, the standard lambda CDM, the constraints on the deviations, when you open the parameter space by 1 or 2 parameters, including non-Gaussianity, which is less weakly related because most of the results were obtained by the 2-point function, but not all. And so now I turn to Planck and other CMB and other probes, so that now we will be revisiting all the rest of cosmology and see whether there is the extent of the consistency or of the crisis. So Planck first with other, I mean, how solid are the CMB? So we've done a lot of work, there's been a lot of eyes on this, but let me start with something pretty simple, which is, this is a map of the 70 gigahertz with the LFI instrument. This is a map with the 100 gigahertz instrument. This is an estimate of the noise that we can have. And then this is the difference between the two. And what you see is essentially the different emission, the synchrotron, dust, and so on, because this is a slightly different frequency. But this is expressed in thermodynamic unit. You see that you know very well the CMB component. Okay, and these are two instruments. So first of all, two technologies, which one of them has never been used before, are giving exactly the same result as this visual. Now you can go a little bit further than this. Now you can do this also by comparing, for instance, what the temperature alone plus the bump at low E of polarization so that you break the degeneracy with tau. But you can also do this with TE, or you can do it with EE, but that's weaker. I mean, it's polarization only, so that signal is very weak, much weaker. So we have to complement it with BAO. But these are three different probes, and essentially what you can see, they are essentially in agreement, right? I mean, you look at the various things, and, well, okay. And of course, the total constraint is the blue one. So, I mean, nothing really remarkable there, apart from the fact that, well, you know, we can actually determine cosmological parameters much better than anything before in three ways, which is good. Now, this is a comparison of the power spectrum at separate frequencies, like the 70 gigahertz from the LFI instrument, that's a noise curve. WMAP would be a bit noisier. And then you see the most noisy from the HFI instrument, the 100 gigahertz, the 123, these are the noise level. And so you see that when you correct for the noise, what you obtain is this, and you see that, I mean, it's completely consistent. So we have lots of, now this is on the frequency space, consistency there. This is also happening now, now I did WMAP, now it's the beginning of ground experiment, they are becoming able to cross-check Planck results. So this is a recent result of, in February, of AT, and you sort of see that the AT result is completely consistent with what we have. Now let's go further. This is essentially the two sites where the future of the CMB will be developed, essentially Atacama and the South Pole. And for now, the two leading experiments in the world that are also the basis for the future are, well, at the South Pole, there are SPT, which is a 10-meter telescope, so very high angular resolution, as well as the BICEP and Keck arrays, which you've heard about because this was the low L possible detection that turned out to be dominated by dust of the BMOs. In Atacama, it's the ACT experiment, and then a sort of medium-sized, sort of 2.5-meter polar bear. And so you have essentially most of the CMB experiments on this, plus CLASS, which is the PI led by the PI of WMAP, and which is trying to do the very low L from the ground, which is very courageous. Okay, so let's look at that, and you can sort of look at these two experiments. ACT, okay, this is a field. Let's take a field of Planck, and let's compare with the same field as rendered by ACT at the same frequency. What you see is, well, ACT is completely consistent. I mean, it's just like a less, I mean, Planck is just noisier. Well, of course, I mean, it's, the signal to noise, which is 1 at L over 1600, and we are 8 much higher there. And there is very little cosmological signal on scale smaller, as you can see. I mean, at the small scales, I mean, you are not adding small scales. It's just a noise in the small scales. It's just still damping that we're seeing. Now, you can do this with SPT, and of course, SPT cannot see the large scale because it's a small field, and Planck cannot see the very small scales because it's a small telescope. So what you can do is, rather than comparing directly SPT and Planck, you high pass Planck so that you remove small scales, and you low pass SPT so that you remove small scales, and you take the difference. And this is the rendition. The only thing you can see is a point source, which is variable. So it's been taken at 2 different times, so you see a point source. So already at the map level, you have excellent consistency whenever this is possible. Of course, Planck is doing this on the full sky. So if you look at, say, for instance, error bars as compared to SPT, you see that Planck completely dominates. The error bars are much smaller, all the way to L 2000. So what we're seeing is that the future is now the high L small scales will be improved, in particular in polarization, by future experiments. But for now, this is all consistent. For instance, there was an analysis that was done also by comparing various cross spectra, either internal or with Planck. And what you find is, well, this is a distribution in simulation of what you could expect, the distribution, given the noise levels and so on. And that's what the data, the actual measurement of these cross spectra gives. Obviously, this is completely consistent with expectation. Now, of course, you do have to be able to do things. If you go to much smaller scale, there is a tendency to a shift with SPT. I mean, at L greater than, when you go to a much larger L max, if you include in the analysis, there is some tension, 3.2 probability to exceed. But that's also the scales where it's becoming increasingly difficult to be making those measurements because you have to control your beam with the exquisite level, and you have to cope with foregrounds which are becoming more and more dominant at these frequencies. So there is something you can do though, which is look at the difference of the spectra and see how consistent this is. And you see these are the expectations for all couples of pairs, and this is the data. The data point is here, it's complete, and so this is a way to remove cosmic variance. So this is a much higher, a much stronger test of the consistency of the data, because you've removed cosmic variance that can hide quite a bit of differences. Okay, you can also do this specifically on polarization. Yeah, that was what I was alluding to. I mean, this regime is where foregrounds like SZ and so on, point sources, starts to dominate. So the CMB on those scales starts to be a very small part of the signal. But this is still consistent. I don't want to spend too much time, but anyway, this is a global picture. The Planck points are in blue, so TT, EE, BD we have only indirect things, the phi, and TE cross correlation. And so, well, essentially, this is all the CMB measurements, and they are essentially all consistent. And now to show you that we still have Planck has pretty much done the work for TT. We measured 1.5 million modes, But in EE, we measured barely 1/10 of this. And in BB, I mean, maybe a few tens of modes globally. So the future is obviously there. We have all of those modes, which are carrying a lot of further information, which you cannot see from there, but I know you can do analysis to see that you can continue to improve the constraints on all parameters, so you can decrease the size of the net so that you can catch more fishes. So that's going to come.
But which parameters will benefit more, if any?
Essentially, well, you benefit those that are more degenerate, but then you have to go back to, we have those plots. We'll do this offline if you don't mind. Okay, so now so I think with CMB, I mean, there was a phase where there was some surprises about the Planck results, and so there were people that suggested that this might be, related to some unknown systematics in Planck, and the more time goes on, the more unlikely this appears to be. So, okay, so I'm going to try to walk you first BBN, which is sort of higher Z, and then we'll move toward low Z. So BBN, you have the data points, the constraints on helium and deuterium, which are from the various observational constraints. You have the BBN calculation as a function of omega B, as you know, and what you see is omega B within lambda CDM given by Planck, and the consistency is really excellent. Now it's true that there are some reanalyses that have a small push, so you can sort of see the kind of leeway that is left. But of course, so it's really cool. I mean, we're measuring things at very different times using very different physics, and we essentially get to the same answer. But of course, the thing that is not shown here is lithium. And lithium is discrepant quite a bit. And it's been from WMAP days, it's always been discrepant. And this has been revisited again and again and again. So the last one I saw was in February. This is this one. I just quote the sentence: in the absence, of course, of major undetected experiment blunder, nuclear physics uncertainties cannot account for the cosmological lithium problem. And so discrepancy now amounts to 4.6 sigma. So that's, I'm sorry?
Can I make a comment
Sure.
on that? The point is that there is no cosmological lithium problem. I've discussed this at extent with the speed. I understand.
Wait.
But I think it's important to stress that the lithium that people observe is in the atmosphere of stars.
That's what I'm saying here.
Okay.
If you can wait, there is a long-standing thread of uneasiness regarding the observation of, more precisely, the relationship of what is observed to what is inferred, which is the true primordial. So for instance, there have been people, French experts like in Toulouse, that have been claiming for about 20 years that if you were to do a better calculation of stellar interiors and so on, there would be essentially no problem. So there are uncertainties about a turbulent regime in the inner part of the stars, which make it, uncertain. Let's put it this way. But if you say, no, that's not true, well, then you have to find a theoretical explanation. And so one of the latest one I saw was alkany. So, well, that's already old. That's December, 3 months ago. So they're trying to kill two birds with one stone. So I'm just giving this as examples of, the kind of work that people are doing on the theory side to actually try to find various solutions out of some of the hints. Some are pretty serious on the face of things. 4.6 sigma starts to be, it's not like a 2 point something. I mean, this is, so we do have to solve this as a community. There's no question. But this may not be fundamental physics. That's all. And that's what you pointed, and I'm perfectly happy with the comment. Now, it's just to show, this is Alkany's paper. I realize I have lots of material, not enough time, so this is for your perusal. You'll keep it, and there are a number of things I'll go fast on, because otherwise we need to come back tomorrow for another 2 series of private lectures. Tau. So tau. Tau is a measure of essentially the Thomson scattering all the way from the observer to the last to reionization. Now, you remember, as I said, The universe becomes neutral at the redshift of about 1100. It's the dark ages, and then first stars or first light emitters come in and reionize the universe. In the process, you damp some of the fluctuations and you create some new ones at large scales. And that is the signature of this bump. And depending on the optical depth, which is shown here, the different values, you get, well, a bump at very low, L equals 10. Remember, L of 200 is 1 degree. So L of 20 is 10 degrees. So this is really very large scales. And this is very small. Again, the peak in this unit, my contribution to the variance is at 6,000 micro-K square. We are talking of, 5 10^-2. So this is really hard, and this is the limit of which Planck is not a cosmic variance limited measure of tau at this time. It's essentially one of the two main goals of the LightBird satellite that is being studied right now by the Japanese and others. Of course, the problem here is that if this is the central value, you see the cosmic variance given a small number of modes is very large. So we don't have that many modes to play with, and usually determination will be just scattered within this large bump. So it's a really tough measurement. Anyway, so it sort of shows, if you change tau, in theory, you see that how it damps, you can sort of see how it damps the temperature, the polarization, and creates the E mode. So that's the natural place to look at, but that's very tough still. And that was just what I was telling you about, 0.02 typically being the amplitude. Now, if you take the Planck measurement, which is best fit of the order of 5 10^-2, then you can deduce what is the free electron fraction, and you compare with the constraint that we have, and things seems to be fine. And that's not the trivial result. At the time of WMAP, we claimed that there was a much larger value of tau. There was essentially a conflict because there was no way. With usual model of star formation and so on to create that high tau.
WMAP 1.
Yes, and then I'll show you the story in a minute. So anyway, here are things which are more for the experts, but depending on either the priors or the shade that you fit for how you reionize and so on, you can have slightly different constraints. These are the posterior distribution for tau, and you see, for instance, if you assume that you describe reionization with other 5 modes in principal component analysis, or you assume that this is the 10 hyperbolic tangent shape, you get slightly different results. But that sort of gives you visually, by how much this change according to that hypothesis. So this is a history of tau. So that's what you were talking about. So there is WMAP 2013. So this is, it doesn't go back all the way because we are kind. We don't show the values which were around there in the first release. But essentially, it seems that we are stabilizing to pretty low values. And the next stop bit is essentially LightBird to improve on this. Now, just a quick side thing, which is not a primary thing. If you think of if dark matter can annihilate, then you can inject energy that can heat the medium and that affect the free electron fraction. So you can actually, you can compute things. That's something that Sylvia presented in Ferrara in 2014 in our one of the first release. And so you can just look, this is the effect that visually, the kind of impact this has when you do this. But these are for, you can see for yourself. So you look at the various constraints, and the latest one is here in unit of 10⁻28. This is, we just have an upper limit. We don't find, say otherwise, any indication of dark matter annihilation at that level. And that's interesting because that you can compare with the various, where this should fit, if this is the explanation of a number of things that have been proposed as explanation for...
Sorry, Professor.
Yes?
The plot is independent of the mass of the dark matter.
I have no idea. I think...
Maybe a comment?
Yes.
That's my paper. So that's actually it's the generating sigma V and M, in annihilation cross-section and mass. That's exactly why you have that line, because that's a straight line in sigma DNM. The constraint comes basically from the amount of ionization that you inject, because that's the generate we talk. You rule out the parameter that is in the previous slide, which is 2, and then you have a cut like that. D-degeneracy is slightly with the channel, so it annihilates entirely into electron, plus and minus, plus and minus, etc. But the good thing is that, can I keep going? The good thing is that all those things over there, they depend on the dark matter profile in the objects that you study. For the CMB, the amazing thing is that it's a smooth cosmological background. So that line will never move because there's something you fundamentally don't know. It's the
that suggests that the rest is at coffee. Okay, now let's move to low redshift. Now definitely redshift smaller than about 1 at most. So this is a neighborhood, quote unquote. So baryonic acoustic oscillation, what is it? Well, it's essentially remind you that we say that the evolution due to the photon pressure was essentially acoustic oscillations in the primordial plasma and so on. But this does not disappear, and it actually shows in the distribution of galaxies the echo exactly of a sound wave. Now this is due to this change of release of PowerPoint. This little movie doesn't work, unfortunately. So that's what I just discovered, and I didn't find a way to fix it since yesterday. So anyway, so you can sort of just do the calculations, see how you propagate a sound wave, and when these things becomes transparent, you do find that there is a particular specific distance at which the propagation freezes at late time. And so while you have the usual so in the CMB that shows, you see this oscillation. One way is to stack things on peaks or trough, and then you see the various these profile. Now these can also appear in the distribution of galaxies, and if you look at the correlation function, there is a little bump at a distance, or if you prefer in the power spectrum, you can see oscillations. And that's just the same physics completely. And the beauty of this is that since now we are just looking at the distance between peaks or trough, this is a very solid measurement, which is much harder than most of the other cosmological measurement to screw by some systematic effect that you haven't seen. So it's probably one of the safest that we can have. And so oh yes, I did put that slide. So for instance, if you look now in terms of power spectrum of the three-dimensional distribution of galaxies, you do find this oscillation when you remove the sort of mean, and you see this, and you look at the characteristic scale there, and then you can compare with, for instance, Planck. And here it is. These are the 1 and 2 sigma corresponding angle as compared to all of the various measurements. You see that there is the latest in the game is the one at higher Z. That is, well, that's like 2 sigma or something. So of course this is the one where we have the least experience about potential systematic effect, but in total, it essentially says all experiments agree very, very well. So that's agree with the prediction. Agree with the prediction of the CMB when you use lambda CDM to do the expansion, the extension to today. Of course, CMB doesn't measure things at that redshift. Now let's look at supernovae. Supernovae, I remind you, what you are measuring once you standardize the light curve of the object by applying some actually empirical laws, just completely empirical, about the shape of the light curve versus time. You normalize, you have an excess, you think that once you've done that, they all correspond to the same absolute magnitude, so then when you have a redshift you can compare, and that gives you relative distances. So these are the latest take on the data, and this is just a bean version of this, and this is compared to with a 1 and 2 sigma expected from Planck within lambda CDM.
I did not understand. What is
this? Is just the distance modulus x minus the distance modulus expressed that you expect in Planck in lambda CDM normalizing Planck.
Okay.
Right? It's nothing else that this, if you want, this curve obtained with lambda CDM with the parameters of Planck.
Okay.
Right? So this is just a prediction. It's just the same thing, but now applied to relative distances. And the only thing you can see is, well, there's just absolutely nothing to see. Planck is completely consistent with supernovae. Of course, there's another step, which is you may want to normalize the supernovae and then get a value of H0 and so on. I'll get back to this later on. And I want to get there, so that's why I'm rushing it a little bit, because, but supernovae themselves, if you're not normalizing it, then with Cepheid, it's perfectly fine. Okay, redshift space distortion. Well, that's another thing. Another effect, yeah, it's really Cosmology 101. Okay, we use redshift to give distances to objects. But of course, what we actually measure, the reddening or blue shift, can be contributed also by a peculiar velocity of the object within a line of sight, right? I mean, there is a cosmological effect. Say, you know, at low z, the fact that you can express these as an expansion velocity, if you wish, which would be h, the Hubble constant, times the distance. But of course, you have the peculiar velocity. And this has two effects. And if you look on the line of sight, an object, and if you imagine you have a pancake or something that is crushing, then you have velocities like this, right? And so, of course, this has a specific effect. So you distort the pattern. So this is called redshift space distortion. And this pattern is proportional to how far the velocities are increasing. So it's actually essentially a probe of the growth rate, which is something that is specific, in particular to GR. And so you measure something, you can have access to this F sigma 8. Sigma 8 is a normalization, so that's the same thing. It's related to the amplitude of the spectrum, the primordial one. And this F is essentially, D is the linear growth rate, so this is the logarithmic derivative of the growth rate. This is the data that you can, and you can sort of have access to this because you are looking at how the correlation between objects changes when you are looking transverse to the line of sight. Yes, transverse versus the longer line of sight. So this is this elongation that this difference, if you measure along the line of sight or perpendicular to the line of sight, that gives you the magnitude of this effect of distortion, which is then within GR, giving you this F, and then you can express these various measurements in this form. And this is the 1 and 2 sigma prediction of lambda CDM normalized by Planck. Pretty good, isn't it? All of this, if you remove any of these assumptions, all hell breaks loose. That's the interesting part. Now, you can also do something where you are measuring the shear of images, and you can look at the correlation of shear as a function of distance between sheared images of distant objects, right? I mean, you look at galaxy, you feed ellipses to them, and then you will see that there are correlations, because in particular, if you have a blob there, and then the galaxies will tend to be elongated along at the fixed radius in the direction tangentially. Okay, so you can actually look at these various correlation functions. These are the data, you do the measurement in various beams and so on, and then from this you can then compare with Planck, and essentially you find that this is the Planck full correlation, and these are DES lensing. This is the blue thing, and if you did DES plus Planck, and Planck lensing only, you get this. Now that's acceptable, even though kids are actually pushing these ellipses. I mean, this is the same type of experiment, but it increases the distance, so it's a little bit less good. Now, this is not to worry too much, but there's something else. With these galaxy surveys, you can also look at the correlation function, the standard correlation function, no shear, just galaxy clustering. And if you do the full analysis of this, when you also use the galaxy clustering, then you have an increased tension. But then you have to cope with bias. I mean, you know, this is a clustering of luminous objects. So I think that with lensing there is no real tension, but there is one, which I think you're diving into dirty astrophysics, so I'm not overly worried for now. Now let's keep moving. So in essence, you see a lot. I mean, this is a humongous amount of work. A large part of the community, I mean, is involved in, each of them is a big collaboration with burning a lot of telescope time. Each of these points is really expensive. But what you see emerging, and for somebody that did his PhD in the 80s, I used to see scatter plots, and everything was just, one thing was always disagreeing with the other. This is just unbelievable. I mean, the level of agreement there. And it's including statistics, you don't have to remove anything. I mean, so what I say is there is a mild tension, okay, when you include galaxy clustering. I mean, that's written. Don't tell me that I didn't warn you. It's there. Now, remember, this is only, in essence, the mean. I mean, we're just checking here mostly the mean evolution. Although, at least certainly for this. This is actually not quite true because this is already perturbation theory. But here, this is really something amazing. You are seeing the power spectrum evolve linearly as of today. So it's the actual one that we measure is actually slightly different. There's an increased amount of power. These are the nonlinear corrections to account for the actual power spectrum of the matter distribution today. But the linear part, which can be deduced, it's essentially this. And you see that temperature, polarization, lensing of the CMB, cosmic shear from DES, luminous red galaxies clustering, Lyman alpha forest, all of those are sort of telling you, well, this is at different scales and different times, they all agree for the same curve. And remember, these points are measured. You have to convert everything to the same scales. And of course, since at a different time, you have to do this using cosmology. So the raw point that you use, you have to shift them in the two directions, okay, to get there. And there was a plot which I don't have, that was done by Tegmark years back, where you take the same point and you just change the parameters, and then you see how the points just scatter all over the place. Now this is a much higher resolution, much higher precision version of this, where when you dial in specifically the Planck parameters, it all fits together. That's pretty impressive that we've come a long way. Now let's keep moving. Okay, so neutrinos, they are, in the Planck analysis, the standard is that they are essentially some of the neutrino being at the minimum 0.06 EV. We don't have the level of precision that we have to actually differentiate. Do the small mass splitting. But they do have a number of effects, and they are relativistic at early times, so they contribute to the radiation density. And so NF is something like 3.04, where 3 comes from 3 neutrino families, and the 0.4 comes from essentially, you can explain this better than I do, but that doesn't matter, which are not completely decoupled at the electron positron annihilation. Anyway, so this has an effect also because, one of the effects of that lead to the specific shape of the CMB is the fact that photons from the last scattering surface had to propagate through potential wells, right? And you can think that if it's not special conditions, a photon will fall into a potential well. The potential well has evolved by then, so when it goes out, it will be redshifted or blue shifted depending on the evolution. Okay, so that's an effect that depends on how potential wells are evolving after the last scattering surface. So that's called essentially integrated Sachs-Wolf effect, and you have different periods where this happens. So when you vary the neutrino abundances, then you have effect also on the detailed shape. Okay, that's one of the things. And then, of course, the influence of the amount of lensing you have. And if you go to very small scale, then they can free stream away. They're essentially depleting the amplitude of the fluctuations on small scales. So all of these, I mean, all of it, again, this is all standard physics. This is described in gory details in books and so on. I just want to sort of give you a hint that, yes, this curve is actually determined by the detailed balance of a lot of effects, which we can use to actually probe them.
It's also a shift horizontally because of if you increase radiation in the sink.
Probably so. I mean, this may not even be complete. Anyway, so that's a basic constraint of the sum of neutrino mass here, H naught. The implication, if you draw samples, they will. Of course, this is an attempt to show the third dimension. So this is sigma A, the normalization, which is the projection of the amplitude, AS, the scalar amplitude, propagated to today, to be able to compare with, say, galaxies and so on. And so, well, what you see is that without BAO, you have it's pretty degenerate. You have, if you don't consider constraints on sigma 8 or H naught. Now, as soon as you add BAO, you start breaking the degeneracies, right? Because it's a different redshift, and so what you find, it's, let's see, this is a dashed blue line. So here, the constraint goes there. So you see that it's a considerable tightening, and so that's in action, you know, something where you see a degeneracy, which is a geometrical yes?
The dots
dots are all, it's a Monte Carlo sampling on the posterior distribution, right? Now, what they are, so you just show the density, is the density of points just is proportional to the posterior distribution, but, and usually you just, you know, you can feed contours and so on, that's all. Putting the dots allows you to sort of show what are the other parameters, or some of the other parameters that is needed to have an acceptable feed. And so you see that if you want to have a very low value, you are in the blue, so you have a very low sigma. That's what it is. So you have here essentially, you know, the inverted versus normal hierarchy and so on. You see the constraint, and you see that you get a factor of 2 by adding the BAOs. So that's really not small potatoes. I mean, the BAO are crucial. And so that's why it was important also to verify in the first place that, you know, there was consistency between Planck and BAO within the framework that we have been proposing. This is the same thing on NF, okay? But now you can sort of see that if you look at H naught, you see that there is a local determination, which is by no means direct. It's called direct, but it's only not direct. But you see that there's an obvious tension. Okay, but so we'll just record this, and I'll get back to this later on, because I mean this is a serious one, and we have to discuss it. What else? Oh, by the way, yes, you see that also. Well, it should be pretty obvious. The standard value is here, and you see that, well, it's only completely consistent with the standard value. So there is no sign, as there was at some point in WMAP, there is no sign of NF being non-standard. Well, I want to skip this. I also want, there is still something that is really cool among the extensions. Again, there are constraints. You can go even further away in terms of model, adding a sterile neutrino, testing perturbation in the neutrino background by changing the way they contribute, changing arbitrarily, not physically. Okay, let's be very clear about this. Normally, the neutrino, I mean, behave as free-streaming particles. So, in their contribution to the stress energy tensor, I mean, they should be modeled with the effective and these are just consistency parameters. Effective speed and viscosity, and it should be one pair in both cases. But you can sort of say, let's just play with that, and let's say whether there's another contribution, but the standard neutrinos, to the stress energy tensor. And what you find is completely consistent with the standard values. So even things which are like, you know, the contribution of neutrinos within the standard model to the stress energy tensor is actually testable, and that just holds fine. Of course, if you insist on, I mean, there are things, I told you yesterday that now Planck and some of the constraints, like in particular the LSR plane, was now immune to a lot of the extensions. But I just want to remind you that this is not a completely blank statement, that this will be true for every single model forever. Here is an example of a model which is just says that, well, you would have quite a shift of the constraining power if you completely change the model. Well, yeah, that's pretty obvious. So I just wanted to give this grain of salt as compared to yesterday, where I say, well, you know, we reduce, you know, essentially all of the WMAP results on NS were not robust to changing any of those that I showed you yesterday, right? Like omega k, like W, like all of those. So Planck has completely broken these degeneracies, but not all of them. So I want to be clear on this. Omega k, well, all right. So we've made quite a bit of progress on this. You know that there is a well-known degeneracy line on omega k versus omega matter versus omega lambda. Very first determination, and that's the one I alluded to the first day, was already we were seeing that omega total was close to 1. I told you, well, it's not. I mean, the constraints are relatively weak. As you can see, this is 0.4. So, but it was enough to really disfavor the omega m equal the omega total hypothesis, while omega m was shown to be 0.3 by direct measurements in the 80s. So there was quite a bit of evidence that omega total was 1, and so that was starting to say, well, maybe we should have something like omega lambda. This was refined pretty quickly, and now this is a Planck result, which I will show a little bit better here, and we'll get back to this in a second. So this is the degeneracy. So the degeneracy line is slightly off. Let's see. The degeneracy line is here. I don't know why for the 2018 we didn't plot this again, but anyway. So here are the Planck results when you use temperature, the full TTTE, but you are not using lensing. Okay, so that's important. Of course, you shouldn't remove it, but just to see where the various constraints are coming from. So you see that there is a long degeneracy line. As soon as you put the CL55, the power spectrum of the recovered lensing through the cross correlation between the various L's, the thing that you remember, the dark matter map that I showed you. Well, as soon as you use this, you break the degeneracy, and you are narrowing into this. And now when you use BAO on the top of this, that's how you get the very tight limit that is mentioned in the plot here, which is really amazingly tight. But you can notice also, and this has been noticed including in Nature paper, not noticed, but commented about, because it's been noticed for a decade, that the central value is more about, some open universe, or some closed universe, around, say, maybe 0.05. Okay, it's a weak indication, as you can sort of see by yourself, right, because this is exactly along the degeneracy line. But if you just take the best fit and without any grain of salt, you would conclude that, there is curvature. We will get back to this. Now, all right. Now, of course, lambda, as you know in this audience, is a conundrum for all of physics. And so people have been thinking, to see what we should do with it. Should we go all the way to the extreme of, things that personally I'm not so happy with, like the landscape and so on, and we draw dices and so on. But you can also, standard answer has been to introduce dark energy, and depending on which physical model you put behind, you can have a long series of specific changes to cosmology. And if you are even more brave or interested, let's see, you can actually look at modified gravity model. Of course, modified gravity is just like a non-Gaussian. Non-Gaussian is Zeldovich used to say, yeah, non-Gaussian is like non-Dodd. As an animal, that's not a very precise specification. And there's not a so well-defined framework. There are several frameworks to try to parameterize deviations from GR, and I'm not going to have time to go through all of this. But so, well, one way, among others, is to sort of say, well, as compared to the standard equations that you get, like the Poisson, you imagine that the Poisson equation is modified by an arbitrary factor, mu, of time, A is the expansion factor, and space, K. And you modify also the sleep equation. And so that's one way to, out of 5, or maybe you're saying 5 minutes. 5 minutes. So this is just an effective description, right? And so you go for it, and well, okay. So let's use the simplest possible thing is just to say, well, dark energy is actually just parameterized by an equation of state P over rho, which has a parameter W, which if it's undistinguishable from a cosmological constant is -1. So there is this well-known degeneracy of the CMB. You cannot really, with CMB alone, tell the difference. What Planck has been doing since 2013 has been to break this with BAO, and then you see that, well, you are pretty consistent with -1 and something which is like 0.33 for omega n. There was, in the earlier release, some tension with supernovae. That was the original these contours were initial supernovae measurements. Now there had been a reanalysis, quite extensive, by Stolnik et al., which now is a Pantheon survey. And with these corrections, these are now the latest constraint they put out. This is not us. I mean, they're completely independent, and that's another one, which is the bull's eyes is -1. So no indication. Well, by the way, yeah, so that's, that was, okay. So that was the indication that maybe there was, an unstandard W a while ago, and when this came out in 2017, essentially there's just no more indication. And so you can see that CMB can be, the degeneracy can be broken either by BAO or by supernovae with equivalent result. Now you can go one step further. You say, well, no, it's you want to have something dynamic, so you will have an equation of state. This is 1 out of 10s, okay, but that's one of the simplest, which is it's like an expansion at low z. And if you just take Planck result, TT low E plus Lansing, you get this. Clearly, the best fit is phantom dark energy and so on. But that's pretty weak. I mean, that's one of the things. And so you ask, well, all of these data sets which I've shown you before are being consistent on the standard parameters. Well, let's use them and let's see what they go for. And essentially, they go for something that is indistinguishable from lambda. Okay, so you get, oh yes, I gave the numbers there, and then you have different tables, show you the variation of chi-square. So if you really want to look at those slides, well, it's there. You can even have a no a priori reconstruction in beams of Z, of W of Z. And there again, well, you have no sign of, it's not very high precision, but there's no sign of any deviation. Now, let's, I told you that we could parameterize the deviation from GR with these two things. Well, if you assume, well, it's still too much, the data is still not able to constrain the full space of possibilities. So typically what is assumed is that these deviations as compared to GR are not scale dependent. So you just assume there is no K dependence. And you further assume, this is typically what people do, that the deviation as a function of time is just proportional to omega, the energy density contribution from dark energy. So you do this, you see that this is a kind of variation. Bad news. This goes essentially at very low L. Very low L, cosmic variance, it's not going to be uber constrained. Right? And the other big thing, of course, because you are testing sleep, is the lensing. This is phi-phi. And there is a big variation. But we are at the early days of phi-phi. Remember, I mean, Planck is amazing. We did this, I forgot, now it's 40 sigma determination of the existence of lensing. But this is just the beginning. I mean, what we'll see now will be very tight constraints on CL phi-phi, and so this will be improving considerably. Still, here where we are, here are the constraints on mu and eta today, and well, typically that's what you see, right? So that's a place where the introduction of additional data doesn't change dramatically the value of the constraints from Planck. The numerical are given here, and I will conclude. I'm giving one more slide before stopping because this was one topic, which is, well, we can have yet another approach rather than trying to parameterize in a totally sort of theory-free, which was the previous one, which say, well, let's introduce some arbitrary function of time and space to the standard equation of the GR. You might actually want to write an action and then use EFT, that is to impose some symmetries and blah, blah, blah. You do all of this with the sort of most general that you get is 9 function of time. Damn it. I mean, we are very far from being able to constrain this. So so there we have to accept to restrict to more specific models, or Horn-Destiny models and so on. Then you can sort of reduce this to essentially 1 function of time, but it's still too much. So you actually specify a particular variation with time. So, I mean, we are getting desperate here. I mean, that's pretty tough. Still, once you do this remaining parameter that you have, it's essentially completely consistent with lambda CDM and GR. Okay. But, again, this is not uber constraining. I mean, let's face it. But nevertheless, it's just amazing that we actually can use, always the same data set to put these further constraints. So I think, these are give you the numbers. And to finish, this is the last slide on this topic. One thing that is interesting is you can also look, I mean, you look at this form, you can sort of say, well, I have cubic operators. Well, I'm going to have contribution to non-Gaussianity, obviously. So we can actually look and search for, it turns out that the cubic interaction terms generate 2 specific shapes, you remember, of the previous, I told you, the shapes, or the orthogonal, the so-called orthogonal shape, the local shape, and so on. So on these 2, the specific one have a pretty strong commonality, they project, if you wish, on the already existing shapes that we've already constrained on ortho and equal. And so we can use this to actually constrain some of the combination of parameters there, and that's given there. Of course, this is still completely compatible with GR. But I find it interesting because this is the beginning, we are starting the beginning of an era where we can actually use non-Gaussianity to actually start probing, the various possible terms of extensions beyond GR. And I stop here. Yeah, I need coffee.
So we have up to 1 hour break in the cave.
Yeah.
Okay.
Okay, so far I essentially went through to say everything is rosy, everything is amazingly consistent. There are some small tensions here and there, which are not, of course, if you are a professional, you worry about this, even sort of two sigma things, like I told you about the low L lack of power, that might be the sign that there is maybe a characteristic scale in the inflaton field and so on. So, of course, we worry about all single little things, but on average, there is nothing that really very noticeable. Well, there is one exception. So, for instance, you can compute you deduce what is expansion rate versus redshift again, within lambda CDM normalized by Planck, this is a perfectly well-defined thing. This is, again, this 1 and 2 sigma line. And you already saw some of the constraints, and now here it is. You have the Reese point, and I mean, remember, for Planck, this is 1 and 2 sigma. So this is really pretty far away. Now, if you want to get some numbers, Planck in the standard lambda CDM, so for now, I'm talking basic lambda CDM. I'm not opening the Pandora's box of the various parameters, right, for now. But I already commented on that, the previous case, where I showed you how H naught varies with various hypotheses, and I told you that that didn't really work. But so for now, we are having at something like 4.4 sigma discrepancy. So that's starting to be pretty serious. Now, as you let me just go there first. The way that the usual, which is nothing but direct, H naught measurements involves essentially 3 steps. And one, you are trying to find the distance to Cepheids by geometrical means, parallax essentially, so that's pretty safe. And then you use, I mean, since the Hubble days, the fact that there is a period luminosity relationship for the Cepheids. As you may recall, by the way, that at some point H naught was 600 kilometers per second per megaparsec, because it was realized shortly after, in the Hubble days, that there were 2 types of Cepheids. And, well, when you were taking this into account and using the proper period luminosity for the object that you really had, it was reduced to, I forget exactly, 150 or something. So there is a long history. But anyway, so once you've done that, you know the distance of the Cepheids, so now you can calibrate the luminosity period relationship. And then you can use this when you find Cepheid inside supernovae to sort of calibrate in terms of supernovae, and then you are in the Hubble flow, and corrections like the peculiar velocities and so on are clearly negligible. So that's one way of doing it. But remember, I also told you supernovae are perfectly negligible.
François, sorry,
yes.
I remember last year in Sexton there was a discussion about exactly the Cepheids, and there was a...
but I'll come to this. Oh, don't, it's coming. Oh, well, no, not quite. No, not the peculiar velocity thing. No, unfortunately. No, what I have is the local star formation rate effect. Sorry. Anyway, so I remind you that the distance, the h of z, if you wish, of supernovae, or the distance modulus mu, is in perfect accordance with the redshift dependence in lambda CDM. I mean, that was one of the plots I showed you earlier. So you can think of doing something else, which is instead of trying to determine h naught by calibrating the supernovae at low z with Cepheids, you can try to find something else that will calibrate the supernovae, and then instead, in that case, you actually look at what is the h naught value from that. And one way of doing this is to use BAO, because there are BAOs in the same redshift group. But of course, BAOs, they need, it's just an angle, right? So you need to input a physical scale. And usually the way this is done, which is our drag, essentially the acoustic distance all the way to some specific epoch, which is very close to recombination, then you can feed that in, and that sets, so there is, you use the CMB, it's not independent of CMB, to give a physical scale that sets the distance of BAO, which you can use to calibrate the supernovae, from which you deduce h naught. When you do this is what is quoted here. Where is it? Let's see. Yes, it's here. So when you use CMB lensing with BAO, you deduce something which is completely in accordance with Planck. So you might still say, well, this is called inverse distance ladder, because here, instead of normalizing the supernovae by an anchor at low z, the Cepheid, you do it at 0.2, 0.3, but as I say, this was criticized by the fact that, well, maybe this is this is wrong because you are still using supernovae and maybe Planck is all rotten and so on. So first of all, you don't need a very high precision determination of RD, which is essentially the peak. This is related to the peak-to-peak distance. You can use the WMAP data and you get the same constraint. So it's CMB, it's not Planck. So then you can sort of say, well, all right, but maybe CMB is bizarre. So you use actually something else. You use the baryon density from BBN. Well, plus the deuterium measurement, because otherwise you wouldn't get the constraint on the baryon density. This is the previous plot I just showed you. There again. So now there is no more CMB. Okay, now there is BBN, and through BAO and SN determining H0, and that's again a low value. Okay, so now this is not anymore CMB, but that's still early universe. That's why people talk about early universe versus late universe, because you need to find a way to calibrate the supernova. Now, so that's one thing. Now, on the other camp, there is something else, which I think I know. Here, time delay for multiply lens images. So, as you probably know, we have a number, not very common, but now we have 6 of very high quality multiply image quasars, and you see them there. So these are big campaigns and so on in very high angular resolution. And what you can do, and that's been done by a number of people, in particular by the Holy Cow collaboration, is you look at the luminosity of each of these objects and you monitor it with time during a very long period, years. So now you can, and so you see there are variations. So there are variations which are stochastic, which have to do with micro-lensing event passing by and so on. Forget about this. So then you sort of set, you look at the common part, which is the same thing up to a time delay, because each path from the quasar in the background is actually a different path, and so it takes a different time to travel that path. Right? So you are essentially seeing the same curve displaced by a certain time. So after lots of observations, they finally get the various delta t's of these images. Now you can do now a model of the lens by using all of the various constraints, and if you have arclets, this is even better, so that you can now find that this delta t up to coefficients is proportional to H0. Because this is essentially, H is essentially sort of the scale of the overall prime. You know, you have the lens, the source, the lens, the observer. So you scale the prime, and that scales delta t, of course. But to get a numerical coefficient to get H0, you have to do 2 more things. You have to have a lens model, and then you have to sort of see whether on the path, there are not some additional small things along the way, like galaxies, potential wells, and so on, which are adding some uncertainty. So they do a lot of work to actually do very deep images to try to map all the sort of interlopers, okay? And then they do a mass model. And for the mass model, unfortunately, there is a degeneracy. You can add a sheet of matter, and that doesn't, all the results are you get the same images. So then they have to find another way to break the degeneracy, and they use now essentially velocity dispersion inside the lensing object to put an additional constraint. Once you do all of this, and you think that you propagate all of the errors properly, and that there is no more residual systematic effect, each of the objects leads to a posterior distribution, which are given there. So you can see this is the latest. There are 6 of them, and they have quite a bit of dispersion. They're pretty wide. But if you have essentially equal prior, then you just do simple statistics, and you get 73 plus or minus 1.5, 1.8, whatever. So that's the thing. Okay, so it's also fairly complicated, and well, lots of pitfalls, but they think that they are doing it fine. Now, let's go one step further. So, if I go back here, oh, why is it doing, yes. So I'm trying to summarize, this is a summary of last summer. there was a meeting in the Kavli meeting. So you see that you find, well, all right, so Planck is well, it's Planck within lambda CDN. I mean, okay, of course, right, so it's there. Now I told you DS plus BAO plus BBN, it's also there. So when you normalize the anchor, you find it there. Now you have, let's see, where is it? Shoes. So this is a result, the original one, which started the whole mess. Okay, it's here. Holy cow is a thing that is, I just mentioned. And now, so in June when I was organizing this Cosmo Gold conference at IAP, Wendy Freeman was there and she refused to, she said, well, pretty soon I'm going to have some news. So it broke out just afterwards. This is the value that she got using a new method to calibrate, which is not Cepheids, but tip of the red giant branch. It's well, there is some stellar physics that tells you, well, there is a maximum luminosity and so on for certain type of stars. You can go after that and so on. So this is again a way to find a standard candle. When you do this, you get 70, which is essentially in between, and if anything, it has more overlap with the sort of so-called early universe value. Now, 2 weeks later, after this, after she sends this, there is a paper by the Shoes team that says, no. These people, which have just been working only for 30 years on H-naught, they don't know what they are talking about. They forgot a big thing, which is a blending bias. Now you are getting into, I'm getting thin on this. But say, no, if they haven't done properly their conversion between the various filter. Yeah, a standard nightmare in astronomy is that, you know, filters were done, they were used as a system on some observatory, some other observatory will use a different system. So the problem is how you convert one observation in one filter system to another file system, so you have to do cross calibration and so on. This is dicey. Of course, that depends on the spectrum of the object, because the integral within the spectrum, within the filter changes. So, okay, this is dirty astronomy, but that's standard. They claim that the actual, it's not 70, it's actually 72.5. So this claim that a world specialist of the other team is actually wrong, biased by 1.4 sigma. I mean, this is unbelievable.
The Yuan claim is about the Reese data, right?
No. Yuan is part of the Reese team.
Okay, and it's about which?
About Freeman team. Wendy Freeman, the H-naught project on the Hubble. On Hubble. Yeah, on HST. Okay, so these are the historical. Yeah. You know. So, well, when I saw this, I sort of say, wait. I mean, when we have world specialists that still on this move and bias at the level of 1.5 sigma, how can I judge? I frankly, I'm not going to comment further. But of course, very recently, so a few weeks ago, Wendy told back, and she disagrees. And she said, no, these guys don't even understand what we're talking about. And so she claims that now she's even refined further her error bars, which are now not 1.9, but even 1.7 systematic plus 0.8. So this is a final say from Wendy's group, which is, well, 69.6. So instead of 69.8, so it's slightly there, plus, I mean, okay. So that's the situation. The so-called direct measurement, in my view, is a little bit of a mess. And it's very hard to, well, if people that spend a life on this one topic can't agree, I mean, the only thing I can sort of say, well, I'm not prepared to throw out all of cosmology on the basis of this. Let's put it this way. It's still not it's not, what?
It's probably just a loose cable, like with the faster than light neutrinos. No, it's just that.
No, but that's, you've seen all the steps and so on. Now, there is something of interest, because still, you know, I mean, even though we don't understand the Cepheids, we don't have a physical model. It's the sense problem than supernovae. I had one seminar on Cepheid physics depends on plenty of parameters. This is actually quite complicated and so on. And there just appears that there is an empirical relation that, but you know, maybe there are different class of Cepheids again and so on. How could I tell? Now there is indeed a criticism by a French guy that has been working on supernovae for a very long time, Michael Rigaud, which is actually making the following point, which is the supernovae, they have actually a dependence on the local environment, actually the local star formation rate. So you imagine if depending on the galaxy you are in, and depending at which place in the galaxy, you may have different local star formation rate. He has been studying this. It's a well-known effect. There is a dependency on the absolute luminosity of the supernovae on that particular point. Okay? And so point one. And the second point is to say, well, it so happened that all of the supernovae that Reese is using, all of them that are used to calibrate are in young environment. While those that are used for the orbital measurement, well, I mean, some at high Z, they are not young. So there is a bias, he estimates it, and essentially, when he corrects it, it becomes compatible with Planck. Again, what can I say? I'm just saying that people that have been studying this to death are actually claiming that there is a systematic effect that is not accounted for. So he has been saying this 2 years ago. Reese counter-acted on this. He found some new argument against it. So it's all about, you know, estimating an effect which even Reese and Skolnick and so on all agree is present now. They say it's not existing first, but now they agree that this exists, but they say it's too small to explain it. So that's as much as I can to sort of present the various lines of evidence on H0, but let me just, so that summarizes it pretty well. So that's also pretty recent. That's, of course, this is done by Wendy Freeman, so this is also in February. So I did my homework in preparation for here. So this is Planck. You see the DES supernovae. You see the Reese Lansing Cepheid calibration of supernovae. You see the Lansing is actually, it's not Lansing. I think this is the gravitational delay, the time delay of multiple image by Lansing quasars. It's there. You also know that gravitational wave emitters can also be used as sirens because we can look at the period and so on, the models. Unfortunately, the error bars are such that this is the constraint, because there is essentially one we can use today. It's promising. It's very interesting because it will take a few tenths to be able to start to play. But of course, you need to have a gravitational event that is in a place that you can locate, so you can have the redshift. I mean, so you know the story. And then there is the TRGB, tape over the red giant branch by Freeman. And, so that's the situation today. So you can judge for yourself what should be done. Frankly, specifically in my team, we spend a lot of time, but also in George's team in Cambridge, at hammering the Planck data to try to find systematics and so on all kinds. We are pretty confident. And everything that I've seen in terms of cross-check with other things so far makes me even more confident. And then there are the additional ones of using just BBN and so on. So frankly, the systematics explanation in the so-called early universe, I think it's uber unlikely. So you are left with either you trust really strongly that, you know, what I described the best I could about this so-called direct measurement, which are the local measurement. In that case, you have to invoke new physics. Find a way to reconcile the two. So, well, fine. After all, let's have a look at this. Well, there are yet another constraint that just appeared. I just want to skip it because otherwise. Okay, so, well, there is a pretty obvious thing you can do. Is let me just go back one step. Where is it? Yeah, the supernovae, okay, they start about that redshift, right? So that's the thing where you have really consistent story without any complexity. You have just all the supernovae, so you can trace the H of Z. This is the same thing that I showed you here, right? But one way, graphically, is just to say, yeah, well, there is a late dark energy that just suddenly pops up, and essentially you're becoming, it's not lambda CDM, it's now dominated by a new form of dark energy that suddenly sort of, you know, this curve sort of goes really fast. Why not? You see that it has to behave exactly as lambda CDM all the way to a redshift of, say, 0.3 at most. And then suddenly, once, of course, conveniently we don't have any probe, then the equation of state changes radically and the curve peaks there. So, well, that has been proposed, several steps. So, for instance, there is a recent paper by Lee and Shafilou, which just say, well, phenomenological emergent dark energy model. Okay, so I'm trying to give you the idea of the kind of things on the theory side that are being proposed to try to explain the tension. But there is also a very recent paper by Benevento et al., which is also February, which, you know, they look at the detail. They say, well, suppose that there is indeed this dark energy picking up at very low Z. It will still screw up the calibration of Cepheid versus supernovae. And their conclusion is that doesn't work. So even that solution doesn't work. And actually, most of the community is convinced that this is not the way to go. Now, the problem is, okay, if you don't do this, you don't want to screw up all of the great agreement that there is between, say, temperature, polarization, lensing, and so on in the Planck data that has been covering to death with you. So to preserve all of this, you have to keep fixed a number of scales. Otherwise, you know, the scales all change. And you can, I don't want to walk you through in detail on this, but essentially you have to, you know, the sound horizon, the distance that the sound wave can travel has to be modified by 7%. This is absolutely huge. And there is only one time that you can do this. It's a decade of redshift before the moment where the universe becomes transparent that you can do this. Before it doesn't do anything, after that it just screws things completely. So, well, how can you do this? Well, there has been essentially, for now, two possibilities. Interacting dark matter, and the other one, I understand that Christian Wederich was actually a lecturer here not shortly before me. He proposed a while ago, for other reasons, early dark energy. And this is just the idea that you have, irrespective of the detailed physical modeling, that, you know, suddenly you have something that behaves as that has a around W equal -1 equation of state that dominates during a factor of 10 and disappears, rebehave, is dominating, is decaying essentially faster like radiation. So it has to, it's somewhat contrived, right? I mean, you have a window, so suddenly during that window, you have, you know, the beast pops up its head and then poof, it goes down again. But the beauty of this is that you can calculate. And so the first to really propose this as a solution was Vivian Poulin, Schmidt, and Kendrick Smith, and I think Mark Rementowski. So that was the first paper to actually propose this specific mechanism as a way to solve this. Now there has been more papers on this. There is a recent one, Korami Nesdad, which shows you if somebody, I give you this because I see that they give all the intermediate steps. It's very pedagogical. So if you want to look at the detail of this, they do it's nothing else than having another fluid and doing again the standard perturbation theory of NGR. Right? I mean, you do this, and the beauty is here. To explain this, you have to have, okay, so these are the Planck points, okay, EE and TT, again, normalized to lambda CDM, so we are looking at residuals like we've done before. So here are the residuals of Planck, you can sort of see, and here is essentially for a few models the residuals which are necessary to solve that tension. You cannot really tell there. I mean, you cannot exclude this. But the beauty is, with the experiments ongoing now, I mean, they will really improve the E mode. I mean, that's the simplest thing to do. And in all this regime, I mean, these error bars will really be tightened. So we'll know. I mean, that's what I like about this. Is actually, there's a theoretical explanation that we'll be testing very soon. So anyway, I mean, that's just a summary of my take on the H0 tension, which is apart from the Rigaud, I mean, from the local star formation rate bias, the bias of supernovae depending on the local star formation rate, which is a well-defined explanation that I think we'll know. So that's a specific proposal for why the local H0 measurement is wrong. I think gravity wave sirens are very promising, but I'm afraid that they will arrive after the battle. I mean, there are lots of people excited about this, and the time for us to collect sirens where we have the redshift and so on is probably, I hope that we'll know before that. Let's put it this way. And there are no obvious explanations. Yes, I didn't refocus on what I showed you before, which was, NF, all of these things that have been proposed. Yes, you can change the relationship as compared to lambda CDM for the H0 that you predict. But there are effects like NF, but you need it to be much larger than is acceptable for the CMB data. So it doesn't work. I mean, it can change a little bit and decrease a little bit of the tension, but that still remains pretty high. Okay, so let's keep going. So, despite the fact that I spent a fair amount of time, I think there is quite a bit of consistency in all of these various probes, and which is rather remarkable. But now I want to conclude essentially on, and I think that's get into the discussion we had at the question and answer yesterday, which is the so-called A-lens curiosity, which I think allows to a number of take-home messages. So first of all, I want to remind you what is one of the effects. I showed you, I think the first lecture, the impact of the propagation through an inhomogeneous universe on the images. So temperature is a little bit shifted, E is a little bit shifted, B is created even if it's not there. One of the effects of this shift is among other things, to blur slightly all the spectra. Okay, and this can be understood heuristically by thinking, well, if there is a region which is overdense or underdense in a particular patch of the sky, right, that just amounts to scale, roughly the order 0 effect, is just to scale the temperature power spectrum. Well, or the E mode power spectrum, the same thing, right, of course. So when you think of now, if you take the average of all these different patches on the sky, you are essentially, convolving the pristine, no lancing spectrum. And indeed, when you do the calculation, this is indeed a convolution of the unlanced CL by the gravitational lensing potential CL, which I showed you. And so it's an effect that is perfectly well known and that is accounted for when we fit, of course. So when you use COMB or when you use any of these programs, of course, this is all computed consistently, and that's it there. Now, you might still say, this is a difficult way to go after it. But you can have, as I told you, and I hope I convinced you, that you can measure this lensing effect directly, because you remember this is sort of coherent variation, distortion of the image of a few minutes of arc over a large scale of typically a degree. And so you're building correlation that wouldn't be present otherwise in a Gaussian field. So you use this, you compute a 4-point function, and you get CL phi phi, and this is what you get. And this is the predicted value that you should have within lambda CDM. And so you can play the same game and ask, well, could I sort of arbitrate? Now let's add another layer, which is, okay, for consistency study, just to know whether I see the blurring of the power spectrum at the level that I expect, I can just arbitrarily scale the lensing potential in the calculation, in the theory, by some factor, and use it as an arbitrary parameter. So if it's lambda CDM, I get exactly the smoothing that I expect, and then A lens is equal to 1. So it's really just to check the consistency. But I point to you already that we know that the lensing is perfectly fine. When you measure it directly, I mean, you look at the potentials and, well, it's fine. But when you do this, there is a preference for A lens. The smoothing is not exactly what you expect, and there is a preference, and here it is. It's a 2.4 sigma effect. You find A lens equal 1.2 something, plus or minus 0.096, I mean 0.1. Okay, so you see that it's 1.2 and that plus or minus 0.1. This is mostly driven by the temperature spectrum. I mean, it's been known since the first release. I mean, this is not something new. We were surprised by this, so we spent enormous amount of effort on this. I tried to find any explanation, any systematics. This has been really resilient. So our take on this, it's not really lensing, because direct CMB lensing reconstruction doesn't want this. The problem, why am I making this comment? You might say, come on, 2 sigma, 2.5 sigma, why am I bothering you, this select audience, about this? Well, the problem is that these project into small deviations, which are usual extensions, which have analogous effect, this smoothing, and that can be omega k, W, sum of the neutrino masses, modified gravity, they all respond exactly to the same thing. Now, and so you get the posterior distributions if you use just TT. So TT is the blue one, right? So you see. Then you see TE. TE actually wants something that is the opposite. EE is this one. The full thing in black is this one. George, in a recent paper that you might have, has been claiming that his version of take of systematic effects makes it less serious. Yes, you see these are the dotted points. Okay. So yes, we see a deviation. But you see that this is using the baseline likelihood. This is 1.18 when you use not only TT, but the full thing. So these are the values, and ChemSpec, which is the Cambridge version, has a slightly larger error bars, and so this is a little bit less significant. Now, let us look at these famous deviations, which is something I mentioned yesterday. So here are, again, the residual of the Planck data point in temperature binned the ratio to lambda CDM. Okay? And to guide you, this is a power spectrum multiplied by 100. So that's 1% of the actual power spectrum. So these are the residual. And if you just look at this, I mean, you know, well, you don't see very much. Indeed, you see that this is a 16% probability to exceed with 2400 degrees of freedom when this is unbeamed. I mean, there is essentially nothing. It's a perfectly valid fit. I mean, lambda CDM is a good fit. I mean, that's what it says. Now, yes. Now, if you introduce this ALNs, what is it that ALN fits? Well, these are the best fit ALNs, this 1.2 that I just mentioned, and that's what it actually fits. So you see, this is essentially driven by this on one end and a couple of points there. This is actually the same signature of something we spent a lot of time on, which is there was a surprise when the Planck result came out, and there was a substantial shift of parameters as compared to the WMAP ones. The first reaction was, of course, by the WMAP team, this is all wrong. Well, it so happens that you increase the L and you find that, yes, it shifts, and we've done detailed simulation, which you can find. Where is that paper? I thought I had given the reference. Oh, no, that's probably the next one. Yes, here is the reference. So we had noticed in the detailed study that when we were looking at the inferred cosmology using only the low L or only the high L, there was a shift, and that was indeed the source of the difference of parameters as compared to WMAP. So we asked the question, is it statistically acceptable that when you add that many more modes, that you shift by that amount? This is in gory detail, 60 pages on this single point on this paper, where Sylvia Galli was actually the lead author. And it's fine. And you see what is there is this bump here, the best fit lambda CDM on a restricted range is once as compared to the lambda CDM over the full range, you can improve things somewhat, and these are the variation. If you fit lambda CDM only at high L, as compared to the best in the full range, you see also a slight difference. So again, this is again the same thing, right? This is statistically fine. So coming back, so all right. So this was this comment, right? So A-lens is yet another manifestation that yes, there are small residuals which that you can project on A-lens. But A-lens is just one explanation. Look at what is fitted by open models, omega k. Now you sort of say, I'm not fitting lambda CDM, it's one of these open extensions that I mentioned earlier. You fit with omega k. And the best fit, you find that what it fits as compared to the without omega k is the blue curve. The A-lens is the black curve. Modified gravity, the best fit that we have, the modification is a red. Okay, and then you can even do another one about it. So all of this, so what it means is all of the indications which are of relevance for theory, which are of interest, they are all having to do with these tiny residuals, which are, if you are in the language of A-lens, is something at a 2.5 sigma level. Okay? So it's not uber strength, and this is, I commented also on this, on the omega k plot, if you remember, which is when you are along the degeneracy line, yes, you may have a few sigma indication. You throw in something else, it breaks the degeneracy, and it says clearly, no, this is the wrong explanation. It's just a statistical one. I'm perfectly happy with omega k equals 0, all of this. So that's the thing I had said. It's the same thing. This degeneracy line is, you can also see A-lens versus this deviation of, modified gravity, the slip, in the potential. So that's, it just also referring to the same thing. So, part of the study we did, apart from trying to understand where this was coming from, is now you are not using the full spectra, all co-adding. Of course, the spectra comes from co-adding different takes, if you wish. And the way we do this typically is that we start with a frequency map, and we take cross spectra, say, of the 100 gigahertz map with the 143 gigahertz map, or the 100 to the 217, the auto spectra of 100 by 100, and so on. So we start, and what we fit is actually not, well, we cannot fit that directly, so we fit something that is CMB plus foreground. Okay, so we determine, so our nuisance parameters are the contribution of foregrounds, like say dust, the dust spectrum. So what you can look at the best solution that is determined for the same foreground model and lambda CDM of each of the different takes. What, say, if I throw out a good part of Planck and I just keep 100 cross 143, what is it that I get? Or I take another combination. So all of those are different takes, and I just plot them. And what I see is essentially that given our solution for foregrounds, I find essentially exactly, even the residuals are the same, which strongly suggests that this is on the sky. And that's not a systematic effect, right? Because a systematic effect had no reason to be present with the same strength at the same place in the spectrum in different detector sets and so on. it's rather strongly suggests that this is not a systematic and this is actually on the sky. Now, on the sky, you might still question this and say, well, yeah, but I mean, maybe there is a statistical fluctuation in the dust, for instance, which is one of the most important, which is exactly in the same location, because there are plenty of modes in the sky. So maybe I can have a chance correlation between a dust mode and a CMB mode. Now, realization is such that, well, I have two independent processes, the dust in our galaxy, the microwave background. Well, I may have something that is just a chance correlation, so that may screw things somewhat. Well, but then if this is true, the dust is a strong dependence of frequency. So I should see something that is strongly frequency dependent. And the only sign we have of this is at 1450, where at 217 the deviation is larger than the other ones. That's all there is. So it may contribute somewhat, maybe 0.2 sigma or something, 0.3 sigma, but that's not enough. So it's very unlikely that this has to do with chance correlations, which are, by the way, also measured by the covariance matrix and all of that. So I don't think this is galactic dust. So the last comment on this is, okay, well, let's for a minute look at this A-lens issue. Is this really, let's accept that whatever is the reason, modified gravity, whatever, I just use it as a template of some effect. I don't know what it is. Of course, it could be, even if it's a systematic effect, what is it that it does on the other parameters? And what you see, that is when you introduce A-lens, on H0, the tension goes from 4.2 sigma to 3.6 sigma. Well, it's not really great, right? I mean, it's 3.6 is still quite a bit of a tension, but it does solve the small tension there was on the amplitude. So that's essentially the situation. So there was a recent, yes, go for it.
So maybe it would be nice to give this parameter free of varying in the cosmological analysis for model constraints, because really you mitigate this statistical
No,
problem.
I don't agree. But that's a very good question. This sort of amounts to say, if I don't like the data, the answer of the data, that's my theoretical prior, I'm going to introduce an arbitrary template which has no justification whatsoever, and I'll say I'll marginalize over this. Fine, I can get anything. I can fit an elephant. I mean, you are not allowed to do this just for arbitrary reason to introduce a modification, because this is introducing a modification and you paint the modification in addition. You have no reason from fundamental physics or whatever, this particular one. Of course, if I have any justification, that's completely different. We do this all the time. When you look at the spectra, we're not getting the spectra like this. You have, for instance, to correct for the beam, right? The beam, we do marginalize over the uncertainties due to the beam, but we have a physical model. We know that the beams are affecting the spectra, and we know that we cannot correct perfectly for this, so we propagate. In all the results, there are propagation of all these things that we can think of. There are other things like temperature to polarization leakage, the effect of the uncertainty of the windows. That's what we do for 10 years of work for 100 people, is to propagate all of these uncertainties. But you cannot just say, I don't like the answer, so I take a random thing that I just no scientific justification and I just marginalize over it. You can't do this. I mean, you have to live with a lack of comfort that this creates. Of course, we comment, I mean, we have been very transparent about this. We have been showing all the details. You can see this under the hood. So it's not like the community is not aware of it. But I strongly resist the idea that, oh yeah, without any justification, we just marginalize over something that I don't like. I mean, that's You don't spend, 28 years of your life just to introduce an arbitrary, thing that to change the result. But I mean, I understand. We had that discussion over and over internally. I mean, I thank you to ask that question, by the way. No, I mean, seriously, because it's a fair one.
No, because it is related with the Neutrinos and curvature. So maybe when we constrain this parameter, we must discuss about.
Yes, you may say that the constraint on the neutrinos, I mean, are fitting. I mean, if you're okay, my advice is I would take seriously all the results that don't depend on this. Right? I mean, if you are fitting this, well, you have to be taking the result as indicative with a big grain of salt. That's what I would say. That's not going to change. I mean, you still find that this is, NF is still around 3 points. I mean, you don't modify the broad picture. But if you get to depend on that level of detail, I'd be very careful. That's... Now, I want to conclude on this. I mean, recently there was a paper, Valentino, not Do, of course. Well, he was a postdoc, two offices away from me, so I should know. Okay, so they decided to focus on the one particular way of expressing these residuals, okay, which are, so they say, well, this is one way to solve this, to fit this residual is through omega k. And so they go and through and comment about this omega k. The problem with that is that if you insist on doing this, you have a pretty heavy price to pay. You decrease by 2.4 sigma, essentially, I mean the length, constraint. But then you are increasing considerably the tension with the normalization. I mean, now it's not like 2 sigma away, it's like 3 or 4 sigma. The fit, which you had on the angular distance with BAO, is completely screwed. I mean, you remember, it was going through this, right? So the price that you have to pay to ease this sort of 2.4 tension, which can be quite statistical, is you have to sort of essentially throw out quite a number of other probes, which are completely different from one from the other. The lensing from Planck doesn't like it, as you remember. The lensing doesn't like it, BAO doesn't like it. So then this is a question of Occam's razor. I mean, in the end, you just say, well, to help to ease on some tension, I prefer to create tensions elsewhere. So, and the only option, it's the tensions there cannot be explained statistical. If you see this, I mean, you have to say all of the BAO is misunderstood. It's just all BAO is to be thrown out as a constraint. Well, you can choose to do this. That's why they say maybe a cosmological crisis. And they don't say anything different. I mean, mass cosmology, the assumption of a flat universe could therefore, if you say I insist that the solution is omega k equal minus 0.07, then it's a crisis because I have all of these other probes that become inconsistent, which is a fact to acknowledge that yes, really all of the other probes don't want that explanation. That's, that's just another way of presenting things. More recently, there has been a vigorous reply to that paper by George F. Taffew and C. Grattan in Cambridge. And I just, as I said yesterday, they made 3 points on this. Well, one is, of course, they comment on the fact that you have really, they don't say Occam's razor, but that's equivalent. They mention that the constraint is not exactly the same when you use ComSpec, but that's irrelevant. I mean, that's essentially the two likelihoods have been proposed and set out to the community so that people can judge the level at which the constraints are depending on specific analysis choice, which different people can make differently. So this is sort of the level of the residual systematics that you can have. You cannot do better in some sense than having teams that have worked for years that are sort of analyze the same data. In the end, we agree on nearly in temperature. The agreement is at the 0.1 sigma level. Well, as you can sort of see, you can get differences which are nearly 0.5 sigma. Okay, so that's essentially the level of the residual uncertainties in polarization. But that's beside the point. I mean, yes, you can change slightly the significance, but I think they also make the other comment, which I really think is interesting, is when you are along the degeneracy line, your prior is very important. And so depending, the data is not very, what it means when you are at a couple of sigma is on the posterior, it means that you are quite dependent on the prior. And the prior is very weak. What is your prior? What is your theory measure on the value of omega k? On the number of E-fold of inflation. As you know, for instance, on R, that another usual thing is do you make a prior uniform in R or in log R? Well, of course, the data is supposed to be strong. I mean, if you have a solid answer, the data is strong enough to, you know, update the prior to do the posterior strong enough so that you have a consistent answer. If you are starting to have your data whose posterior is very sensitive to the prior, so I gave other examples of this at some other point. If you remember, I also showed that there was statistical fluctuations at the time of WMAP. I did that for, let's see, FNL local. There was a time with a number of modes in WMAP. The data was not very strong. It tolerated, you know, the best fit was actually a non-Gaussian determination, right? That was the best fit. Not uber strong, few sigma. Well, there is no revolution. You increase the number of modes, and well, things go back, and the constraint is actually 0. The constraint on FNL, right? So, again, I think it's sort of interesting because we have so many success in this that we're now focusing on the little things that are sort of suggestive, but we don't have, and that's maybe a sad thing, which particle physicists know about. We have an amazingly successful model, much more than I would think. That's why the first was actually the I forgot how I called this, but well, the surprising effectiveness of lambda CDM, right? I mean, I would never have guessed when I started, you know, implying that lambda CDM would survive. I mean, this is just an effective model with funny and ununderstood and unjustified components, and that has an amazing success. And we are desperate for finding a few sigma things here and there to guide us toward, you know, new physics. Yeah, this one I just want to. Okay, I'm going to skip because I think what time? How long? Can you just because I think.
You have still 15 minutes more or less.
Oh,
or say
okay.
10 minutes if you want to leave some room for.
So anyway, I just wanted to make. There is another place where there is some tension, which I what?
No, we disagree.
There is a tension.
There is a tension. Okay, is it a strong one? How strong it is?
It's always been historically above 5 sigma, but never mind.
Okay, so
anyway,
this is
now the time of for the questions.
Okay, so anyway, so there is something that is really cool that I mentioned earlier. You remember that when there is hot gas, well, there are occasional scattering of the CMB electrons on the hot gas, in particular in clusters where the gas is typically 1,000,000 degrees. So that creates a spectral distortion in the direction of that object. That's called the Sonier-Zeldovich effect. Well, actually, that is a thermal one. There is another one, which is due to the fact that clusters can move. So this is the kinetic Sonier-Zeldovich. So Planck was the first essentially cluster machine like this. So here is a distribution of the SZ effect over the full sky that Planck did. And so you see clusters there where essentially, what?
Beautiful.
Yeah, I mean, it's an amazing one. So, I mean, for many years, I mean, SZ was just an effect that we were all learning about, but, you know, there was essentially no indication. I remember I arrived in Berkeley and I started to look at this, and I sort of said, you know, I'm not going to work on this. I mean, it's no fun. There is no data. So I can do any theory that doesn't work. So I went to do strings instead. Anyway.
Not a big improvement.
Yeah, well, I think they were more fun. That was the point. And I thought this was more like it. Anyway, now, well, I think it's, before I comment on the, there is some tension that is arising from the number counts of clusters. That is, and in essence, it's pretty simple. If you change the amplitude of a primordial power spectrum, you build more within the same model. Old structures have more, start from more larger fluctuations. So if you essentially clip something at a particular level, you have more objects. And since this is an exponential tail, this is a very sensitive thing. So you can, the number of collapsed object of a certain mass is actually a relatively sensitive probe of some cosmological aspect, essentially the abundance of matter and the normalization. That's normal. These are the things that control these number counts. Now, how do you actually use observations to do this? So people in the X-ray have been playing this game, and if you want to do cosmological counts, you have to do a number of things. You have to sort of look at a number of objects of a certain mass scale within a particular density contrast as a function of redshift, and then this is a function like this, which depends on cosmology and so on. So that's how you make the relationship with cosmology. But now you have to give a mass. We don't measure mass directly. So you have to sort of find a way of connecting your observable, which is, for instance, the Sonia-Zeldovich effect, the amplitude of that effect, to mass. So you can try to do this by comparing, for instance, with X-ray clusters. Use scaling relation that have been pre-established, and that's a way to make the connection. Plus, you still need to do another thing that you need to do very carefully, which is the acceptance function of your experiment, which is, of course, you have to sort of know whatever Y is there for real of the sky, how well do I render it in my experiment, and of course this might be a dependence of the particular Y value, as well as the sky location as well. So you need these three elements. Okay, so doing this, initially it was done, we found that there was some tension. So as you can sort of see, omega m, the total amount of matter, and the amplitude of the fluctuations. So that's, which are the two things. So the CMB tells you that omega m and sigma h should be there. And some of the early measurements, deduction, sorry, from number of counts were there. And this relationship of mass versus observable is actually so uncertain that we put, that they put, or whatever, people doing this analysis put a bias parameter. We say, well, we don't understand it, but the detail of the physics makes that the tracer is biased, so we calibrate this on simulations. No, yeah, that's reality. So depending on the hypothesis you do on the detail of this, on how relaxed clusters are and all of these things, on average, you have a different inference on what is the value that omega m and sigma h should be given the number of counts that are observed as a function of the SD parameters. And this is quite a good representation that different group of people doing cluster analysis go from a pretty substantial tension to no tension at all. So that's representative of what the status. I think it's also, at the bare minimum, the Planck data has highlighted the fact that the inferences that you have on clusters really depend on details which are not very well mastered. Different group of competent people actually give different results. You can also, so you may, this leads people to, for instance, think that maybe this hydrodynamic bias is a function of redshift and so on, that is, there is new physics, that you have new physics, new dirty physics, not new fundamental physics, I'm talking gastrophysics. But then some other people come in and say, no. I mean, actually, if you actually correct in detail for the selection function, this is all perfectly consistent. Even very recently, so it's a relatively recent paper. People are trying to, instead of using a several-step calibration using X-rays, you can actually look to the lensing effect of the cluster. The cluster is nothing else than the ball of matter. So indeed, it will distort specifically this area, the CMB itself. So, or background images. So you can actually use the lensing effect to actually try to weight the clusters and then find a way to normalize this. And so that's another example. Of course, you don't measure the bias, 1 over it, and so on. So again, this is sort of telling you that there are a lot of there are not that many, it's very hard to obtain absolutely clean, low redshift observables. And the cleanest we have is really the BAO with supernovae. And sorry, this is also, so that's why when you were prepared to throw out all BAO to solve a 2.4 sigma tension, well, some people are pretty reluctant to do this. On the other hand, well, we lived with this tension on the cluster physics, which, I'm not too unhappy. This is complicated. It's not very well mastered yet. So it just says that yes, the structure formation in the nonlinear regime is a problem where we still have a lot of progress to be made. I want to skip this, and I want to finish on the cool thing. Just one cool paper that is pretty recent. You may know that there has been, I'm really now into the gastrophysics thing, but well, given the abundance that of baryons in the universe that we deduce, for instance, from the CMB, you can say, well, is this consistent with what I directly observe? I can count stars, I can count the amount of gas, say through X-ray and so on, and I can add up and see whether I get to the cosmological value deduced by other means. When I do this at low Z, it jumps. You find what you expect. And you can sort of say, yes, baryons are these fractions inside gas clusters, in this type of galaxies, and so on. That's all fine. As soon as you go to slightly higher redshift, this is a so-called missing baryon problem. We don't know where they are. We don't observe them. Actually, we think we know where they are. We think that actually there are these less dense filaments that are in between the clusters that contain some tenuous gas. And this gas is relatively hot, but less hot, so that's, it hasn't been compressed as much as in the clusters. So it's essentially undetectable in X-ray. So we think that we know that actually the so-called missing baryons at high Z are actually within the filaments mostly. But that was still very recently a purely theoretical hypothesis, which I have no doubt that this is what happens, but it's still theory. So one thing that has been done for a while now, and this is the last incarnation, they made a refinement which I can discuss if you wish in private, but it's very thorough, the technical improvement. What they did, or redid, was to say, let's take the catalog of Planck clusters, this thing, and let's take every pair, you scale it in distance, and you all superpose it. So it's not stacking of the overdensity of one object or blob or whatever. It's actually stacking pairs, right? I mean, you take all the pairs and you just and you rescale them. When you do this, well, on average, you expect to have a filament on between them, right? So you can, now you've stacked all of this, and you can sort of see, do I get an SZ signal, which is precisely the presence of hot gas. And here is a result. When they do this, well, you have to separate from also what is industrial. So you get this for YSZ, and you look at the profile that is determined when you go along this axis. These are the two clusters, of course. This is what you find. 0 in between the filament will be there. This is an 8 sigma detection of the missing baryons. This is cool. I mean, I didn't have any, worry that we wouldn't find. I knew that we couldn't detect them. Well, it's done. And again, I mean, this is another indirect thing that. So it says that the Then you have the Lowick parameter for the warm interstellar media is this value, and that's enough to account for the missing variance. So that was just like, so even things that are totally impossible to see, they actually jive in detail when you go and look at the data. So that's, I thought that this was cool. And let me conclude on two things. So first is, well, all right, so where are we post-Planck in terms of cosmology? So observational. I would claim that the lambda CDM model fits very well all the CMB data in temperature, E mode, B for whatever we have for now, the phi and the cross correlation. We have no strong sign of any extensions. You know, maybe the biggest things are like at the 2.5 sigma. And I spent quite a bit of time on commenting that all of these were these tiny residuals, which are all related to all the, these are always the same indication, but it's just explained in different ways, but that's the same residual. The consistency has reached an unprecedented level of cosmology with the other probes. I mean, this was, I mean, for those that are old enough, I mean, we always had lots of data sets, a lot more inconsistent. Now, the progress of BAO, the progress of a supernova, the progress of CMB makes that these probes now have reached a consistency level which are really impressive. Inflation has essentially continued to pass all of its generic predictions. It doesn't say that there are no surprises, because you might say, well, why is it that we have a potential this way, and why do we start inflating in these positions? But these are theory problems. I mean, as an effective model, it works. And all the basic things like it's mostly adiabatic, yes. I mean, we have strong constraint on isocurvature. We have pretty strong constraint on omega k. We actually found the deviation from scale invariance that was predicted by Mukhanov and Chibisov back in 81. So all of these are there. And so what we are really after now, there is one really interesting possibility that we'd like to go after is the potential detectable presence of primordial gravitational waves, aka tensor modes. Of course, there is no guarantee that it's at a detectable level within the next generation. It's simply that if we were to detect this would be really extraordinary, because it would be really telling of which type of models we should focus on. And we could argue that this is really the first true manifestation, I know that not everybody agrees, of quantum gravity. I mean, Slava would argue very strenuously that this is already a pure quantum gravitational effect. So I'm not going to enter into this, but everybody agrees that the detection of the tensor mode would be really fantastic. But you've seen the constraint, and now we are tensor to scalar ratio at the level of 0.06 at 95% confidence limit. You need essentially, I mean, Starobinsky model or so on, they are more like 0.002, so that's a long way to go, because you have to constrain the foregrounds at the level which is amazing, as well as any systematics in the measurement. So this is really measuring nano-Kelvin fluctuations now. And so now, in some sense, the micro-Kelvin fluctuations of this generation, I mean, it seems like a simple thing. Now we want nano-Kelvin. So there are lots of plans on this, which I want to say a few words on. Oops, yes. Oh, I should have done that. Well, anyway, I'm just commenting, so it's fine. I just press the on-off button with my feet without willing it. Yeah, anyway, no, but don't worry, it's on again. Anyway, so what are the series of lectures I have prepared for tomorrow and the day after is about the future of the field. And so I can say a few words on this. There is no accepted satellite project to do for polarization what Planck did for temperature. We proposed it. We were not accepted by ESA. This was called, well, we gave it several names, but Core Plus, whatever, for Cosmic Origins Explorer. So the only project, and space is still a wonderful place because, you know, it's a place where first you can observe the full sphere from the same observation point, well, same, you know, the same Lagrange point. Of course, it's changing, but so you don't have to co-add the data from taken in various hemispheres and so on to cover the sky. It's very stable thermally. You don't have the atmosphere, which is really opaque at high frequency, so which is really forbidding you to do a good job at tracing what dust is doing, because dust is revealed at a high frequency, at frequencies higher than 217 gigahertz, where the atmosphere is opaque. So you cannot observe through the atmosphere. I think the highest frequency you can hope to use is 270 gigahertz, using a lot of detectors. So the only satellite project which is being studied and is under serious consideration is a satellite-led, is a Japanese-led project called Lightbird, and a European participation is being studied for essentially providing one of the two instruments. ESA doesn't want to be the lead on this. France is well engaged in becoming the lead agency to assemble the European partners. And it's even more complicated through policy, so the UK would not give any money directly to France, so it's, we have to have, the UK would provide, and maybe Italy too, I don't know, would directly provide money to ESA that would send it to France. So we're trying to build a complicated structure to be able to do this, but that will do only the very large scales. So there is only two goals. It's not like Planck where you have zillions of things you can do. You will get two numbers. One is tau, the optical depth, which I told you is not the final answer, and you will get a measurement or an upper limit on R. If it's a measurement, and if this is the first to determine, that's probably Stockholm. If it's an upper limit, well, that's an upper limit. So that's on the large scale. On the small scales, I just showed you that there are the two sites which are now ongoing and are the site of what is a so-called Stage 4 project, CMBS Stage 4, which is a collaboration between DOE and NSF. And the DOE national labs in particular would be providing the sort of 500,000 detectors which are needed. Planck was 50, I remind you. So it's a lot more detectors. So you cannot have the same cost per detector. So all kinds of, you know, industrialization problem has to happen. There will be two sites, and that you may have a question on this. You have the Chile site. Has a great advantage that it can cover a good chunk of the sky, much more than the pole. And the pole, if you are just going close to the pole, well, you're just measuring a tiny little fraction, and then you have you can see below the horizon. So it's a smaller piece of the sky at the pole, but the pole is magnificent in terms of stability of conditions. Plus, this is really dry. So very little water vapor, so you can really go deep. So all of this weighted, it's agreed that there will be two sites, which also amounts to the sites followed by two ferociously competing groups. So there might be a connection there. And both sites will likely be equipped with both large aperture telescope, 5-6 meters, to be able to do the small scales, and small aperture telescope like BICEP, typically 40-50 centimeters, to be able to do as well as possible the large scales. The price tag as of now is expected to be quite the cost of a satellite. That is just the construction, the delivery of the construction is estimated at 500 million dollars, sorry, plus about 30 million of operation per year over 7 years. So you do the addition. So it's typically a satellite cost. Okay. And then you have the scientific exploitation cost on the top of it. Computers, all of that. So that's the situation CMB. Clearly, the goals there, which I will not cover, but I mean, it's of course go after the B modes, but of course also have the sensitivity to be sure to be able at more than 5 sigma to tell the difference between normal and inverted hierarchy for neutrinos. I mean, that's a big goal. But the place where, apart from the detection of R, which would be wonderful, of course, is the fact that this would be high angular resolution, high sensitivity rendering in polarization, which means that we'll be creating lensing potential with exquisite precision. And these are essentially in the linear regime. Okay, so this is, again, the thing I like. It's simple mathematics. We can predict everything in great level of details, essentially, you know, without any computers. So we can actually map, with very high signal-to-noise, all the power spectrum which you had, which is just the beginning that you saw in Planck. We'll get this in gory details. So that will have the implication for neutrinos, but not only. So we'll be able to do cross-correlation with traces like infrared galaxies and so on. If we can find, we'll be able to sort of look at the growth of structure and say, for instance, find the bias. If you have a tracer, we will be able to give the bias of that tracer as compared to the dark matter as a function of redshift. This is wonderful. I mean, this is, you know, the plague that we have had in cosmology, which is all this, you know, distinguo that light doesn't really trace mass, and we have to try to relate this. Lensing breaks this, so this is magnificent. So to me, apart from the B modes, I mean the lensing part, I'm super excited about this, and I think that's really cool. On the other hand, the comment on one of the other very exciting things, which is the non-Gaussianity. Unfortunately, CMB will not help that much because, again, this is an argument I gave yesterday, but let me repeat it. Essentially, the uncertainties go like the square root of the number of modes. And you've seen we had like 100,000 modes in E. In T, we measured 1.5 million. So, you know, you can sort of see how many we'll add. You can also add some B modes. When the calculation is done properly, you end up improving by factors of 2, maybe the constraints on FNL local. So we are very far from Maldesina bound, which would be like, we would need like 100. Or typical prediction from, say, multi-field inflation is more in the FNL local or squeeze limit of the order of 1. So for this, the best hope that we have in the short term, and I think I will see this, is a so-called sphere-X satellite, which is something that will provide a spectrum, a 100-point spectrum, in every few tenths of seconds of arc pixel over the full sky. So we'll get very large number of pixels with full spectroscopy, so we can compute the 2-point correlation function, and as well as the bispectrum. And the calculation that have been done show that we should be able to get down to detectable FNL of the order of 1. So that's really cool. Now, the other part where things will be really exciting is the large-scale structure. As you know, there is DES, but this is just DES 1 year. And pretty soon we'll get the result DES 3 years. LSST is coming. We have all of these big surveys which are coming, which will be improving considerably our vision of the low redshift universe. So the BAO will be done with exquisite analysis. And the beauty of this is that in the end, I mean, cosmology is in principle uber simple. You have you have a power spectrum, you give a cocktail of components, you describe their equation of state. Well, then you turn the crank. This is, for the most part, perturbation theory in GR. And this is all related. All these things are just, all of the various things that we can think of are just manifestation of the same underlying thing. So progressively we'll have more and more the realization of the dream of having as much as possible completely independent probes. Well, as much as possible. It's not possible for everything. And that's coming. So one movement that has been ongoing for a very long time, which I think is, well, we can still improve a little bit, is, you know, we have been doing like the equivalent in the particle physics language of next loop order and next loop order. I don't think we'll go much further than that. So we have a big problem to break, which is try to go into the non-perturbative regime for gravity. Well, this one has been resisting all approaches since my PhD. I mean, you know, it's been the big problem that we are all confronted with. So that's one on the theory side, which is how you deal with the nonlinear aspect apart from simulating it, you know, brute force, which we know how to do. That's the other part, of course, is how do we describe the big, you know, fitting function between the dark matter properties and the light. So this one, we are having a poor man's approach. We are essentially doing, you know, functional expansions, and we are trying to, well, describe how this can be modeled, but lacking some really fundamental understanding yet of all the retroaction mechanism and so on in the nonlinear environment. So there is a lot to be made in that direction. The problem seems to be so complicated that I personally look forward to essentially having a practical measurement through lensing and cross-correlation. So this is actually something that people doing the gastrophysics have to explain rather than me spending my time on doing it. And I think I will conclude on one last slide, which is, you may remember that I said lambda CDM was a simple, effective model, but that was depending on a lot of underlying assumptions. And I did tell you that, you know, with Planck, we have been checking many of them, and I just wanted to remind you that, you know, all of this is actually, any of those that you start changing a little bit is already ruining the description of the data that we have. It doesn't take much. I mean, in other words, we're constraining quite a bit. Curvature was one of them, and so on. So, of course, what I presented to you is, I didn't do it alone. So this is essentially the logos of the Planck collaboration. If you want to learn more than what I just told you, you have like 200 papers to go for, which are there. And now they are all out, and the only thing that is not formally published are the likelihood and the parameter paper of the 2018, which we got the referee report, and we are resubmitting within days. The work is done. We are writing the letter to the referee, so the final thing over there. The likelihood code is out. It's your game now. All right.
Okay, so we have not so much time for questions.
So this is a private, so go for it.
No, I have two questions actually, but since I'm the chairman, please.
Yeah, let's have the others first, if they have any.
I have a request for elaboration. We're mentioning the, not discrepancy, but low L versus high L.
Yes.
Can you elaborate a little bit more on the?
Yes. In the course of the test, in particular, of the 2015 likelihood paper, which I personally drove, among the various cuts we did, I mean, we did lots of cuts, like what if, you know, it's in the spirit of jackknife test, what if I drop these volumer? What if I do, because you can, there are several things you can do if you don't know the answer, which of course we don't, you have several ways. I mean, you can go very far by doing null tests. That is, all the things that you can do which are independent of the nature of a signal. So for instance, you have two detectors which are supposedly measuring the same sky, the same frequency. Their difference should be compatible with the property of the noise that you have intuited or computed or determined or whatever. So these are the first series of things which is null test based. The other part is actually how resilient the particular result is to, you know, whichever combination of data you are using. So there, this is not null test anymore. You are sort of saying, okay, let's look at cosmological parameters within lambda CDA. If I truncate my data by, say, time, let's see whether it's another way of doing the null test, but at the parameter level, which is, well, all right, let's suppose I take the first half of the data in the mission and the second half. Do I get the same answer? Which is also a null test, of course, right? I mean, but at a different level. So you can do this. You can also do this for detectors, right? You can try to do this. I gave you some hint, one of the more complicated one, which is once I correct for foregrounds, do different frequencies tell me the same story? And then you can sort of say, well, and then at the final version in this long series where we put 100 pages of this test, you can also sort of say, well, now the data is sufficiently constraining that I can even look only at some part of the scales, the large scales versus the small scales. WMAP could only measure the large scales. Well, we have mapped sufficiently of the low scale, of the small scales, that we can actually just use the small scales by themselves to confront. We found that there was a little bit of a surprising difference. Well, we were surprised, and we thought this is worth pointing out. So there was you know, this famous triangular plot. So I put the reverse of the top, which was sort of to say, well, what if you look at the difference? And this surprised us. I mean, and so we asked the question whether, well, we pointed the readers to the fact that there was you know, a little bit of a difference. This was picked up by another paper by the WMAP team. And so there was this paper written, I mean, coordinated by Sylvia on, you know, well, is this surprising? I mean, because this is the question. I mean, of course, I mean, you are not expecting to find the same exact value because it's a different tape, right? So the question is statistically expected? So for this to be done properly, you have to actually simulate the full thing. So we did, we looked at the various fits at low L, generated possible high L, and compared with what was actually observed, and found that this was actually not that surprising. But then you can still ask the question, what is it responding? Even though that's not surprising, well, that's just a couple of sigma, that's another way of saying it, you still, you are still interested to know what is driving it. And what I've been telling you is, we know another manifestation that we've discovered afterwards is this scale length, and another manifestation is the drive for W different from -1, omega k being rather 0.027 at 2 sigma and so on. All of these are all manifestations that consistent with the 2 sigma-ish, 2.2 or whatever, fluctuation on the sky.
So, if I understand correctly, where is the cut where you call it called low and high? Where is there?
Oh, it's complete. So first of all, it's initially we called it at L of 600 because this was the place where WMAP is losing it in terms of signal to noise. Okay. When we wrote that paper, we decided to make it at 800 because we found that the constraining parameter, the sigmas that you get from the high L and low L, were equivalent when you separate at 800. So we just decided that we'll call 800 so that we separate in samples of equivalent constraining power. That's it. So this is all related to the same thing, and The point I'm trying to make is that this is on the sky, very likely, and this is one of the two surprises. There is this sort of series of things which are small deviation at the 2.4 sigma level, and then there is H naught. These are the two things that, after all of these are emerging, H naught, I give you my point of view, which is, well, it may be new physics, but there are also room for a different explanation in terms of systematics. But that's something where data will be able to decide relatively quickly in several ways, and I gave you one. If this is the early dark energy explanation, the changes that in polarization, which are consistent with the Planck error bars, it will turn out to be detectable by the next generation. So early dark energy is something we'll know about, well, in the next few years. Systematics and H naught directly, well, that I don't know. I mean, I cannot predict when this will be solved. And for the other pile, I think the situation to sort of say, let's throw out essentially all of the low Z determination to privilege an omega k different from 0 will not be tenable very long. And let me conclude on this. At least your question.
Okay, I think we have to stop now. So if you have, I postpone my 2 questions for dinner.
But that's fine. I mean, or we can just, watch or.
Thank you very much, François, for your brave appearance in neighborhood this time.
Yeah.
And not having you the mask during the seminar.
Oh, that's really too much. I mean, yes.